Welcome to this video on Lorentz contraction. Lorentz contraction is that contraction that occurs in an object in the direction of travel when that object is travelling at a high percentage of the speed of light. In 1959, Roger Penrose and James Terrell independently considered what an observer would see if he took a snapshot of the moving 3D object. The position of the observer is perpendicular to the direction of travel of the moving object. They concluded that the snapshot would not show the Lorentz contraction. In his 1959 paper, Terrell states in the conclusion that any hopes of seeing the contraction in a rapidly moving space vehicle or astronomical body must be discarded. Terrell then went on to consider what the snapshot would look like, taken from that lateral observer's position. He concluded on page 4 of his paper, which is actually page 1044 of the journal, that, quote, "This corresponds to the visual effect of apparent rotation. In other words, the object in the snapshot would appear the same as if it were static, but rotated." This concept has now been shown in an experiment by Dominik, Hornof and colleagues in a 2024 paper. The setup used in the experiment is described in section 3 of their paper. I'm not going to go into the details except to say that the setup involves a pulsed laser of 1035 nanometer wavelength. It has a 1 picosecond pulse and its repetition rate is 2 megahertz. The wavelength is stepped down to 517 nanometers. The group used a high-speed gated camera connected to a delay generator. The delay time between exposures corresponds to how far the object would have travelled at a particular speed of light. If you want to delve into the details, I've listed the link to their paper below this video. I should say that any diagrams that follow are my rather poor interpretation of the figures in their paper. Let's consider a sphere travelling at near light speed. Looking at an angle of pi/2 to the direction of travel, no Lorentz contraction can be observed, but the sphere, according to Terrell, will be rotated. Now consider a sphere viewed from the top. What would be seen is an American football-shaped contracted sphere as shown. But Terrell states that such an object would be rotated. So in this image, we see how the rotation occurs under the Terrell effect. In their experiment, the group used a sphere and cube for imaging. The cube was 1 meter in diameter, and gating of the pulse laser simulated a speed of 0.999 that of the speed of light. The cube had an edge of 1 meter and was simulated at 0.8 the speed of light. The cube is not considered in this video. The view from the front of the sphere is shown in this image at 0.9 the speed of light. On the right is shown the Terrell rotation. For points of reference, note the green meridian in both. So far, the images shown have been the theory. Now to the result. In this image, a sphere is shown travelling from right to left as a series of snapshots. The speed is 0.999, the speed of light. The camera position is on the left rim, which is the north pole. The north-south line runs left to right, and the equatorial line runs top to bottom. The horizontal axis is 11% larger than the vertical axis. The bright dots that you can see are the meridians connecting the poles. I hope this video has been a help in understanding Lorentz contraction and the Terrell effect. As I said earlier on, the relevant paper is listed below this video.